right, guys, welcome to our topic, our fourth unit on electrochemistry. I think a lot of you guys will like this unit, and as we talked about before in the live sessions, electrochemistry has to do with the most practical application of electrochemistry are batteries, which we obviously are seeing more and more importance of as they are in laptops, cell phones, cars, and so there's going to be a lot of future employment in the battery industry to make better, more long-lasting, more efficient batteries. Says, I want you to hurt him. Stop returning his calls. Tell him you found someone else. Okay, little lover squirrel there. Okay, electrochemical reactions. So obviously electro referring to electrons, so we see there's an emphasis on the electrons in these kind of reactions. So electrochemical reactions, what we're going to call those are redox. So that's what I'm going to call them from now on. And that's a short for reduction, oxidation, and I'll remind you guys what that means. In those kinds of reactions, electrons are transferred from one species to another, and that's what a battery is able to utilize, is the energy associated with the movement of those electrons or the transferring of those electrons. So in order to keep, don't worry about the equation right now, in order to keep track of what loses electrons and what gains them, we assign oxidation numbers. So I think we did this first semester, a little chart to show you guys how you're going to assign oxidation numbers. So when we assign oxidation numbers, here, we'll just put them right here. So number one, all free elements, pure elements, they have an oxidation number of 0, okay? Meaning, so if they're not in a compound. Simple ions, like sodium +1 ions or magnesium +2 ions, the oxidation number is going to be the same as the charge or the valence. You guys see there is some kind of correlation with, remember we looked at valences to help us to name. Remember, we assigned them valence numbers, and then we could predict the ratio in which atoms would combine. For example, like hydrogen is a +1 and oxygen's a -2, and so then using that, we know that they combine in a 2-to-1 ratio and form water, H2O. Oxygen, you guys see oxygen is kind of singled out because oxygen is such a prevalent element in a lot of compounds. It usually is assigned an oxidation number at -2. Now, there are some exceptions like in peroxides, but I don't want to talk about that right now. Hydrogens are also singled out. Oxidation number of +1, I say usually, and you can also have metal hydrides in which hydrogen would be a -1, but once again, those are exceptions. And then number 5, for a compound, the sum of oxidation states must equal the total charge. Okay, so I'm going to kind of show you what we mean by that. So let's kind of apply that here. So let's say we have a chlorate. Chlorate is a polyatomic ion. You guys see it's an ion, it's got a charge. So let's say we had to assign oxidation numbers to each of the elements. Well, just going from here, there are no free elements. This is a compound. Simple ions, okay, it's not really a simple ion because it's a polyatomic ion. Oxygen, oh, that's our first one. It's assigned a -2. So I'm going to put a -2. Then you look, there's 3 oxygens, each with a -2, so that'd be a -6. Now remember, it says down here, for a compound, the sum of the oxidation states must equal the total charge. The total charge is -2. So then the question is, what -6 equals -2? And you guys agree it would be a plus. Did I do that right? Yeah. Oh yeah. It would be a +4. So therefore, what is the oxidation of chlorine here? It is a +4. Okay. Did I do that right? Oh, no, I'm sorry. That's why I messed up. My bad, guys. I'm sorry. I get the wrong. It's chlorinate's a -1. Duh. Okay. So it's negative. No. I was wondering why didn't make sense to me. So obviously the total has to equal a -1. So what -6 equals -1? It's a +5. So the chlorine must have an oxidation number of +5. You guys see how that can be kind of different, because you would think, based on the fact that it's a halogen, second from the right, you would think it would have a -1 because that would be its valence would be a -1. So you guys can see the oxidation numbers are not always the same as the valence values. All right. So let's look at an equation now, because that's kind of what we ultimately want to look at, are representations of reactions. We want to look at chemical reactions. So let's say we have this reaction. Now you guys look, it's showing zinc reacting with hydrogen ions. Now you guys, obviously the hydrogen ions, this would actually be like maybe hydrochloric acid. It would be actually HCl, but so it would have a Cl there. But let's say the chlorines are just spectator ions. So nothing changes with the chlorines from the reactant side to the product side. So oftentimes what we're going to show is a net ionic reaction. We're not going to show the spectator ions. So just so you guys realize where these ions come, it's not like just, you guys know if you have positive ions floating around in solution, they have to be stabilized by negative ions as well, but we don't show those. So we got zinc reacts with hydrogen ions and you guys see we still have zinc, but you notice something changed. Now we have zinc ions plus hydrogen gas. So first thing we need to do is, when you guys look at a reaction, you need to decide, I think we talked about this first semester, if it is indeed a redox reaction. Are there electrons transferred between the reaction species? So in order to do that, you have to assign oxidation numbers. So you guys look, zinc, it's a pure element. So what oxidation number does it get? You guys look at your rule sheet, that would be assigned as 0. Look at hydrogen has a charge of +1, so what's its oxidation number? It's +1. Zinc has a charge here of +2. What's its oxidation number? The same as the charge is +2. And then hydrogen here, once again, that's a pure element. You guys notice it's not in a compound. And so what's its oxidation number? It's 0. So these are the oxidation numbers. Now, when you guys see an oxidation number change from the reactant side to the product side, that is an indication that electrons have been transferred. That would be an indication that redox reactions happen. So look at zinc here. Zinc went from 0 to a +2. I'm going to remind you guys, I think I showed you this first semester too. You guys remember oil rig? That's an acronym to help us to remember. O for oxidation. Oxidation is loss. Reduction, R for reduction, is gain. So you see here, oxygen went from a 0 to a +2. The only way the oxidation number could have increased, it could have become more positive, is if it lost electrons. So what happened to zinc? Oxidation is lost. Oh, the zinc was oxidized. So the zinc was oxidized. Well, and then look at this other one. Hydrogen went from a +1 to a 0, so obviously it changed. And you guys see if the number got smaller, you guys see the oxidation number got smaller. That's where that term reduction comes from. The oxidation number is reduced. Obviously, how did the oxidation number get smaller? It went from a positive to a 0. It had to have gained electrons. Reduction is gain. The hydrogen here has been reduced. So we see zinc was oxidized, and it said zinc loses 2 electrons, right? You can see that to become from the neutral to the zinc plus ion, and then you see the hydrogen was reduced. So what you guys will find is anytime there's oxidation, there also has to be an accompanying reduction. If something loses electrons, something else had to gain it. If something gained electrons, something else had to lose it. Okay. So, and then it's kind of the reverse. So you guys see zinc is being oxidized, right? So that's being oxidized, we can see because its oxidation number got bigger, it had to have lost electrons. So what could I call zinc? Or here, let's go with this. This will probably be better. Look at hydrogen's being reduced, right? So it's gaining electrons. So if it's gaining electrons, it had to take those electrons from something else. What did it take it from? Zinc. We would call hydrogen here the oxidizing agent. What does that mean? It means it's the substance that caused something else to be oxidized. So get this, guys. Whatever's being reduced, in this case hydrogen, whatever's being reduced is the oxidizing agent because it's oxidizing the other substance, and then it's the reverse. And then the same way, look at zinc here is being oxidized, right? It's losing electrons. So if zinc is being oxidized, that makes zinc the reducing agent because the zinc is causing the hydrogen to be reduced. So you guys see it's kind of the opposite. The agent is what causes that thing to happen. So you guys, here's essentially how a battery works. So essentially there's a transfer of electrons. The zinc is losing electrons and the hydrogen's gaining those electrons. So electrons are being transferred. Whenever electrons are being transferred, there's energy associated with that. Now, if you just carried out this reaction in a solution, you just put zinc in hydrochloric acid, the reaction would happen and you'd form zinc ions and you'd have hydrogen gas. We've seen that before. Now, unfortunately, a lot of that energy associated with the transfer of electrons would simply be lost. And how is it lost? It's typically lost in the form of heat. In fact, if you guys were to fill that test tube when you put zinc in a hydrochloric acid, it's going to get really hot. It's essentially wasted energy. How a battery works is what we do is we separate out the oxidation component from the reduction component, and then we force, you guys notice how there's a transfer of electrons. We force that transfer of electrons through a wire or through another, ultimately the way a battery is formed, and we'll show how it's actually physically constructed. But what we're able to do is utilize the energy associated with the transfer of electrons by separating out the oxidation reaction from the reduction reaction. So, and that's what we call a half reaction method. What we do is we balance the equation of an oxidation reduction via the half reaction method, in which we separate the oxidation component from the reduction component. Oxidation reduction is two separate processes, balancing these half reactions and combining them to attain the balanced equation. So what we're doing here is we are balancing equations using the half reaction method, okay? So you guys here, I have in purple, this is the steps. We're gonna go through this real quick. First of all, you assign oxidation numbers to determine what is oxidized and what is reduced. Secondly, you write the oxidation and reduction half reactions. We're gonna practice that. Then you're gonna balance each half reaction. And then here's the notes that you wanna make particular attention to, which is kind of new, what we're doing. We're gonna balance the elements other than hydrogen and oxygen. Then we're gonna balance oxygen by adding water. This is kind of something new. And then we're gonna balance hydrogen by adding H+. So we'll show you guys how that works. And lastly, we're gonna balance the charge by adding electrons. And then we're gonna multiply the half reactions by integers so that the electrons gained and lost are the same. This will make sense as we work on one, guys, but at least you'll have this in your notes and you guys can refer to it. And then this still continues it. You notice I didn't purplize it. I mean, you can write it down if you want to have all of them, but it says add the half reaction. I think at this point it's gonna become, I don't think it's gonna be hard to remember what you do at this point. That's why I didn't purplize it, but nonetheless, you can write this down. Make sure the equation is balanced according to mass, and then make sure the equation is balanced according to charge. Okay, so we're gonna do this reaction. All right, so we're gonna have the permanganate ion, and then the oxalate ion. Those are going to combine, and what we get is the manganese ion and carbon dioxide. Okay, and once again, these are part of other. This would be like maybe would have sodium with it. This would maybe have potassium with it, but those are spectarians, so we just don't show it. This is actually what's involved in the redox reaction, so that's what we show. Okay, so you know what? I'm gonna, rather than using the notes here, I'm just gonna work it out here because I think otherwise it'll get kind of confusing. Yeah. So this is the same reaction. Okay. So the first thing is, what you do is, well, that's weird. What happened there? That should happen. Okay. First thing is, you probably want to assign oxidation numbers. You know what? You wouldn't really need to. I mean, you could. You remember when we assign oxidation number, we do it to each one. Remember, oxygen is -2, and so 4 times -2 is -8. What a -8 gets you a -1, that would be a +7. And then this is -2, 4 times that is -8. What -8 equals -2 would be a +6, but there's 2 carbons, so it's a +3. And then this one's just a +2. And then this is, you guys, right? Oxygen's -2, I have 2 of them, so that might, and if it's neutral, that must mean the carbon is +4. So anyways, what we do see is, you definitely clearly see now, the manganese is going from a +7 to a +2, and you see the carbon is going from a +3 to a +4. So obviously there's a change in oxidation numbers indicating this is a redox reaction. So then what we do is we separate it into the two what are called half reactions, the oxidation and the reduction. So basically you'll just take one of them. Let's take MnO4, and you're gonna get where it changed, okay? So I got MnO4 negative, I write it just like it is, but notice I'm just showing this part right here. I'm just showing that part right there, okay? So then, and then I'm gonna do the other one. I'm gonna just show this one. So these are what are called the half reactions, and you're just gonna see what makes them unique. Okay, so you guys, the rules, if you guys look at your rule sheet, first thing is you want to balance any non-H's and O's. So you guys look, 1 Mn, 1 Mn, we're good there. But now you'll notice there's oxygens on this side and not on this side. Obviously you have to count for all the atoms. So you guys remember how they said to do it? You balance oxygens with water. So if I have 4 oxygens here, how many waters here would I need to give me 4 oxygen atoms? I need 4 water molecules. When you guys agree that's 4 oxygen atoms, 4 oxygen atoms. But now you would agree, you're like, well, didn't you just add now hydrogens now? Now all of a sudden you have hydrogens. Well, now I got to balance the hydrogens. So now on this side I have 8 hydrogens. So if I end with 8, I need to start with 8. So I'm going to put 8 hydrogens over here. Okay. So now you want to see how many electrons. So now this is all balanced. You guys should see all the atoms are balanced. Now you want to see how many electrons were involved in this half reaction. So now you just kind of add it up. Look, I got 8 pluses. That's a plus 8. I have 1 minus. That's a minus 1. There's one of them, so that's a minus 1. So when you guys agree, that's like a plus 7 on this side, right? And then here was a plus 2. And then this is neutral water. That's a 0. Plus 2 and a 0 is a plus 2. So it went from a plus 7 to a plus 2. So that involved, there's a difference of 5 electrons. So where are the 5 electrons going to be? If I'm going to balance the charges, see how the charges are not balanced. Where do I need to put, and you guys know electrons are negative, where do I need to put, let me see if you guys are seeing all this. Yeah, you are seeing all this. Where do I need to put the 5 electrons? When you guys agree, I have to put it on this side. So, because now when you guys agree, look, 5 electrons, that's 5 negative charges. A negative 5 and a plus 7 is a plus 2. Now my charge is balanced. So, what do you see here in this case? Let me see if you guys can see it all. Yeah, you can, okay. Now look, for this reaction to happen, it required 5 electrons. 5 electrons were gained. You guys see how it's on the reactant side? It's gained. So according to oil rig, you guys, what half reaction is this? If electrons are being gained, oil rig, reduction is gained. This is my reduction half reaction. Okay? That's what we call a half reaction. Now, obviously what I said is, if you have reduction, you're gonna obviously have oxidation. If electrons are lost, if electrons are gained, they had to have been lost for something else, and so we're going to see it on this side. So you guys, we're going to do the same thing. So you remember, you have to balance the non-hydrogens, oxygens. Notice 2 carbons, 1 carbon here. So how can I balance it? I just put a 2 there, right? You guys remember, you just do the coefficients. So now I have, and now you guys check it out. Everything else works. Now all my atoms are balanced. I don't have to do the whole hydrogen oxygen thing anymore, or water thing, because look, 2 carbons, 4 oxygens, and 4 oxygens. So that's balanced. So my atoms are balanced, but you guys remember what else I have to do? I have to balance the charges. So look, I got one of these, it's -2, so that's a -2. This is 2 carbon dioxides are neutral. So it's a -2 and a 0. So there was obviously a transfer of 2 electrons involved in this. Where am I going to put the 2 electrons? If this is -2 and 0, where am I going to put -2 so the charge is balanced on both sides? Wouldn't I have to do it on this side? Right? Because 2 electrons is a -2. What's a 0 and a -2? It's equal to a -2. So the charges are balanced. And you'll see when this reaction proceeds, what's it going to do? It's going to form this and lose 2 electrons. And oil rig says oxidation is lost. This is oxidation. What you guys will always find is, and you guys, you have an electron on one half reaction, you're going to have electrons on one side, and on the other half reaction, you have to have it on the other side. That's the only way you're going to have a redox, right? Reduction and oxidation. So then the next thing said, we need to try to ultimately put these back together. But now what you guys are going to find is, check this out. If you look, this shows the gain of 5 electrons. This shows the loss of 2 electrons. You can't have that, right? It's like, you can't have a gain of 5 and you only had a loss of 2. These have to be equal. So then the thing is, I want to keep the same ratio. All these are ratios because everything's balanced. But I want to change it such that the amount of electrons gained and the amount of electrons lost are equal. So then you think about, you look at 5 electrons, 2 electrons, think about what's the least common multiple of 5 and 2? What's the smallest number that both go into? You guys should remember from simple math, 10. So then what could I do? I'm like, oh, couldn't I just take this equation and multiply it by 2? Right? Because as long as I do it to everything here, I'm going to keep the same ratios. And then what would I do to this equation here? I'd multiply it by 5. Now look what I end up with. So then I'm just going to go 2 multiply all across. So 2 times 5 electrons is 10 electrons. No, you know what? I'm going to rewrite it down here. So look, it's 10 electrons plus 16 hydrogen ions plus 2 permanganate ions gives me 2. You notice I'm multiplying 2 all the way across, and then 2 times 4 is 8 water. Okay, and then what am I going to do on this one? I'm going to multiply by 5. So I got 5 C2O4s. 5 times 2 is 10 CO2s. And 5 times 2 is 10 electrons. Now, you guys, so now I've accounted, look, 10 electrons gained, 10 electrons lost. So now I can put these half reactions back together. So, and you know what? You just cancel out whatever cancels out. Look, if I have 10 electrons I'm starting with and I end with 10 electrons, you guys see how this is on the left side of the equation, this on the right. Or you know what? Here, it's probably better if you just add them together, just so you guys can see it. So I'm going to just basically add everything on the left. So check this out. I got 10 electrons plus 16 hydrogen ions plus 2 permanganate ions. Look, and I still am at this. You guys know this is on the left side, right? And then I'm going to add everything on the product side. And then you guys cancel out whatever cancels out. 10 electrons on the reactant side, 10 on the product side, which is what I want, right? Obviously you have to have the same number of electrons gained and lost. And then, does anything else cancel out? It does not cancel out. So, what you're gonna wind up with here is, so you guys, this is a way to balance it. So then you just take the coefficients. You notice this was our original equation. So what is the coefficient here? You guys look, it's a 2. And then what's my coefficient here? It's a 5. And then my coefficient here is a 2. Well, that's a funky 2. And then my coefficient on carbon dioxide is a 10. So then you just take the coefficients that correspond to the substances. And so in this situation, you guys see, and what was it that you guys see in addition? You notice that it's you got water, which is fine. You guys, a lot of this takes place in an aqueous solution. You just have water, right? Which is not really taking place in the reaction. But then you'll notice you also have hydrogen ions. So what kind of solution is this redox reaction taking place in? When you guys agree it's an acidic solution. So this would be, right, you guys have often heard of battery acid, right? This would be, a reaction that you could use, right? It's, as long as it's a redox reaction and we set up, I still haven't shown you how physically a battery is constructed, but nonetheless, any kind of redox reaction that involves a transfer of electrons can potentially be used as an electrochemical cell, otherwise known as a battery, that we can utilize the energy associated with the transfer of those electrons. And in this case, it takes place in an acidic solution. Okay, we're almost done here, guys. One last, or actually, we're not quite done. One last thing. Not all redox reactions take place in an acidic solution. There's one thing you have to do if it's, this is all the same, so don't worry about this. We have to look at how do we do it, carry it out if it's in a basic solution. So, you guys see, basically we've got the exact same thing, and then we're able to, okay, last thing, okay, so you guys put this, what if we balance it in a basic solution? Once again, so it's different because we don't, you're right, in this case it was an acidic solution, but what about in a basic solution? You know what I'm going to do? We're just going to just write this down, guys. So here's another, I know it looks kind of similar to this, but it's different. You guys write it out. But you notice when you guys are doing a problem, you have to realize, okay, this redox reaction is occurring in a basic solution. So it's going to be different than this one because look, this has hydrogen ions, present. So there's going to just be one extra step with this, okay? So otherwise we're going to do the same thing. And I think you guys, right, you guys remember I did the individual oxidation numbers to determine that in these a redox reaction. Well, let's say you can assume at this point that this is a redox reaction, okay? So then, you guys remember you're going to set it up into the half reaction. So what would I do? I'd put Cn minus, and then I would put, on this side, I'd put CnO, right? And then what would I do? The other one, I'd put MnO4 minus, and MnO2 on the product side. Okay, so you guys remember that, so now we first have to balance atoms, okay? So you guys can see we've got, one second, guys. We've got, first you balance all the non-oxygen and the hydrogens, got CNN, okay, so you can see I just got an O on this side, an oxygen on this side, and on this side, you guys remember how we balance the oxygens? We add water. Remember, we're not really changing the reaction. You understand, by adding water, most of this takes place in aqueous solution anyway. So I got water, but obviously now you guys can see I've introduced now 2 hydrogens that aren't here. So what do I gotta do? I gotta put 2 hydrogens. You guys remember hydrogen by itself are positive ions. You guys see how everything's balanced. But now This is where the extra step is. Notice we said it's in a basic solution. As I'm writing like this would look like it's taking place in an acidic solution. So here's how you do it. You can, without changing the reaction, you remember, as long as you do something to one side and you do it to the other, you're not changing the reaction. So here's what you do. If I have two hydrogens here, what would I do? I would add 2 hydroxides. But look, what I do to one side, I have to do to the other side. So now it's hydroxide. And you guys look, check this out. Why is this? You guys know when hydrogen and oxygen come together, guys, what does it make? Doesn't it make water? Isn't that just 2 waters? You guys see what I've effectively done? Rather than having hydrogen ions present, now all I have is, you guys see, I can just kind of make this like this right now, right? You guys see? And now I just have hydroxide. All right, guys, let's okay, let's just do the same with this. Okay, so look, Mn and Mn, that's good. You notice I just differ by the oxygens. 4 oxygens here, 2 oxygens here, so this one has 2 more oxygens. So on this side, so I need 2 oxygen on this side. You remember what you do? You add water. And how would I get 2 oxygen atoms? By adding 2 waters. But once again, what have I done? I've introduced now 4 extra hydrogen ions, right? That I'm gonna have to balance right here, 4 hydrogen ions. But once again, it's in a basic solution. So you guys remember, how do we get rid of the 4 hydrogen ions? We're gonna add hydroxides to both sides. By the way I'm gonna get rid of 4 hydrogen ions is if I had 4 hydroxide ions. As long as I add it to both sides, effectively I'm not technically changing the reaction, right? 4 hydroxides here, I'm gonna put 4 hydroxides here. You guys see what the effect is? OH and an H come together, form water. I'm gonna form 4 waters. And now I have a half reaction with hydroxides, half reaction with hydroxides rather than hydrogens. Okay, so then you guys see now we've balanced all the atoms, but you guys remember we need to balance the charges. Okay, so then I look, 2 hydroxides, that's a negative, that's a -2. Water's neutral, this is a -1. Okay, so all told, this is -2, 0, -1 is a -3. Okay, here's a -1, and then water is neutral. So all told here, I have a -1 and 0 is a -1. -3 and a -1, how am I going to balance the charges? I need to add electrons. What side am I going to add electrons to? When you guys agree, electrons are negative, so when I add, and the difference is 2, so I'm going to add 2 electrons over here. When you guys agree that 2 electrons is a -2, -2, -1 makes a -3. You'll notice the electrons are here on the product side. That means when this reaction happened to form this, it lost 2 electrons. Oxidation is lost. This is the oxidation half reaction. Okay, we can do the same thing over here. Got to balance the charges. Once again, water is neutral. It's 0. That's a -1. So this together is a -1. This is 0. This is 0. And then I have 4 -1s. That's a -4. So all told together, that's a -4. -1, -4. So there's a difference of 3 electrons. Where am I going to put my 3 electrons? Hopefully you guys realize you got to put it on the left side, the reactant side. 3 electrons over here. Because when 3 electrons would be a -3, -3, and -1 is a -4. Notice the electrons, as you would expect, since the electrons were lost here, they have to be gained here. This is my reduction half reaction. Okay, so then, you guys remember, overall, we have to account for all of our electrons. You guys, right? So now we're kind of starting to look at them together. Here, this is showing a loss of 2 electrons, but this is showing a gain of 3 electrons. You can't have a loss of 2 and a gain of 3. So what do? We have to make sure these are balanced. Choose the least common multiple of 2 and 3. You guys should know it is a 6. So what could I do to this whole equation here? When you guys agree, can I take the whole thing and multiply it by 3? And then if this is 3, how can I get a 6 here? When I take this whole equation, I kind of ran out of room. I'll just put multiply by 2 here, right? We're just going to multiply 2 across and 3 across. So let's do the top one. I know this is kind of nasty, guys, but look, 3 times 2 is 6. So I have 6 hydroxides plus 3 waters plus 3 cyanate ions gives me 3 of the CNO minus ions plus 6 waters. Guys, 3 times 2 waters plus 6 electrons. Okay, now I'm going to do this one all by 2. So 2 times 3 electrons is 6 electrons plus 2 times 4 is 8 waters plus 2 MnO4 minuses gives me 2 MnO2s plus 4 waters plus 8 hydroxides. Okay. You know what? Before, and you know what, I could take all this and then just add up all the ones on the reactant side and then all on the product side, and then it would be huge. But you know, you can kind of see what to do even before. Like I would already start trying to eliminate stuff. Look, I got 6 electrons on my reactant side, 6 on my product side. I just cancel those out. And you remember, those have to be equal, right? To account for all of our electrons. Is there anything else we got? Look, on my reactant side, I've got 11 waters. See? Now check this out. And on my product side, I got 10 waters. So what's the net amount of waters? If I had 11 waters on my reactant side, 10 on the product side, wouldn't you guys agree? Wouldn't you just have 1 water on your reactant side, right? 11 here, 10 here. You have 1 extra 1 on your reactant side. And then, oh, and then also, you guys look, 6 hydroxides on my reactant side, 8 hydroxides on my product side. So what's the net result? When you guys agree, I have 2 more here on the product side. So my net result is 2 hydroxides on this side. And then anything else? Nope, everything else looks good. So look, I'm gonna go 3 CN minus plus my water plus my 2 MnO4. You guys know it doesn't matter which order you put it in. And then I get, on the product side, I got 3 CNO plus 2 MnO2. And you'll notice, look, overall, you guys see we have hydroxides indicating it's in a basic solution. And then, so what would you do? If the whole purpose was to balance this using the half fraction method, I go 3 CN minus. That means this has a coefficient of 3. This one has a coefficient of 2. And then I look here, this has a coefficient of 3. And then this has a coefficient of 2. All right. All right, guys, thanks for sticking it out. We'll see you next time.